So what we want to understand is if we see this bell-shaped curve for these sample proportions, how do we understand the center and the set? So if we have some variable, x is a sample proportion from a certain sample size, then how to distribute? And what we saw in the simulation is a bell-shaped curve coming through. But for this bell-shaped curve, let's actually skip down here in that to know that we have a normal model, we have to pass these conditions here. So we have our independence condition again, so that the responses should be independent. So like the case of rolling the die, it's that each roll is independent of the next. With this, you can always link that 10% condition as well. Randomization, it should be like rolling a die was randomly simulated. If we're choosing from a population, the sample that we're choosing should be randomly selected. And then the big one is, this is kind of the equivalent to our sample size condition. It's where we need to make sure we have a large enough sample size. Like we saw in the simulation, if we have a small sample size, skewed distributions came through, and we don't want those. So what we should have is at least 10 successes and 10 failures. So what we do is we take our sample size times our population proportion, and that should be more than or equal to 10. And then also taking n times the opposite. So remember Q is just 1 minus our proportion, and that should also be more than or equal to 10. So if we were checking conditions for this scenario, let's say checking conditions here, we'd be taking the sample size of 10 times our, 0.1667, and this would have been too small. This would give us a, 1.667, which is too small. That's less than 10, so that's where this fails, and that's why we see a skewed distribution. Whereas if we take 100 times 0.1667, which would be 16.67, that's more than 10, so that one's good. But you also need to check 100 times the opposite, so taking 1 minus 0.1667. And that would give us 83.33, which is more than 10, so we're good there too. And that's why we see that normally distributed curve come out of there. So you need to make sure both of these are more than 10 before we can move forward. So with these conditions, and if we pass all of those conditions, we're going to call these 3 conditions: independence, randomization, and then our sample size. Then what we should have is a nice bell-shaped curve coming through. And when we have this bell-shaped curve, what we want to understand is it's normally distributed, but how do we describe the center and the spread of the curve? So what we saw is when we take the mean, or the average of those sample proportions, which is this notation right here, that's our average of sample proportions. So when we take all of those p-hat values and take their average, it should just be the population proportion. When we start building these sampling distributions, they're going to tell us some assumed population proportion. Like rolling a die, we knew it was 1/6. Other cases, they'll just tell us what they expect. So for us, you just take whatever value's given, and that's our population, and that's our mean. That's the center of our graph. So with that, you're just copying down what they give to you. With the standard deviation, so where this is the standard deviation of sample proportions, what we need to do is a little calculation. And again, this is back to the sampling distribution of means. Not really any calculation for the mean, you're just kind of copying down the population value. But then for the standard deviation, we need to take into account sample size, because again, Smaller sample sizes have larger standard deviations because we're not dividing by as much, whereas if we have large sample sizes, we're dividing by a lot, and this shrinks down. Take this square root, and you take your population proportion times the opposite. So remember Q is that 1 minus, so times over our sample size. And what's going to be very important for this section is make sure all of this is under the square root. That's a common mistake made, is leaving parts out. All of this should be underneath that square root value. So let's go ahead and apply this. So our first example, suppose 60% of all college students are either very satisfied or completely satisfied with their online shopping experience. You decide to take a nationwide random sample of 2,500 college students and ask if they agree, and is it reasonable to use a normal model? So if you're ever asked, is it reasonable to use a normal model, that means check conditions. Do we pass the conditions to move forward? First, independence. Are their responses independent of each other? Or we can use a 10% condition, like our sample's 2,500 college students. That is probably less than 10% of all college students. So we have a small enough sample size that there should be independence in solution. Let's just go ahead and say yes. Responses are independent, or you can use that 10% condition. And that 2,500 is less than 10% of all college students. Randomization. They tell us that we have a random sample, so we know we have that. So random sample means we pass the randomization. Then for this one, this is where we need to do a little bit of math. To check the success-failure condition, what we need to do is take our sample size of 2,500 and multiply it by, they're saying 60% of all college students. So this is telling us a population proportion. This is what they expect is true for all students. Here's our sample size. So we want to take 2,500 times 0.6. We also want to take 2,500 times 0.4, so 1 minus that 0.6, and both of those values should be more than or equal to 10. So for this case, we get out 1,500. In this case, we get out 1,000. So because both of those are more than 10, we pass the success-failure. So checking all of these conditions, that tells us we have a bell-shaped curve. So mean and standard deviation of the proportions, this is where we want to find this mean of sample proportions, which that mean you just take the population proportion, so you just take 60%. And then for the standard deviation, we need to do a little calculation where we take the square root and we take 0.6 times 0.4 divided by 2,500. And this will give us a standard deviation of 0.0098. So we have, if X is our proportion of 2,500 students who agree, because we pass the conditions, we know X is defined by a normal curve, centered at that 60%, that 0.6, standard deviation 0.0098. So now that we have this curve, we can go to GeoGebra, calculate probabilities, calculate cutoff points. So what's the probability that the sample proportion who agree is at least 57%? So we want to use is this curve that we found, and how we know use this sampling distribution of proportions. It's looking for the probability of a sample proportion. They didn't say the sample size, but usually it'll say of 2,500. They'll throw in the sample size, and we're looking for this probability of a percentage, and that's going to be a common theme with these proportions. So what we want to do is look at this curve where we're centered at 0.6 and have the standard deviation of 0.0098, and we want to look at this probability of at least 57%. So 0.57 somewhere over here. And again, with at least, that means this is the least value. So look at the probability above. So we're going to have a large number coming out. We should have this high percentage coming through. So we take this curve to GeoGebra. We want to find this probability of being more than or equal to 0.57. And what GeoGebra will give us is 0.9989. So what this tells us is this probability of seeing this sample proportion of at least 57%. So what you could say is with a sample size of 2,500 students, there is a 99.89% chance at least 57% of them agree. So again, with these sample distributions, you need to bring in that sample size, and you'll have this percent chance of seeing a percentage.